Hey everyone, this is a review of work, energy, and systems. Getting ready for the AP test for AP Physics 1. So, energy has many different forms, but in this class we are just dealing with mechanical energy. And mechanical energy is split up into three types. Kinetic energy, it's often called K or KE. I honestly can't remember what notation I've been using. A lot of people just call it KE though. And we know that KE, the formula for that is 1/2 mv squared. So anything with mass that's moving has kinetic energy. So there's gravitational potential energy, okay? And that is energy stored in the Earth's gravitational field due to an object's position. So it's really an interaction between the Earth and the object. So I'll use PE for potential energy, put a little g there for gravitational. So that's equal to the mass of the object times little g, which is basically the strength of gravity, and then h for the height above some sort of reference level, usually ground level. I don't want to overthink that, okay? So that's pretty easy to make, or easy to use. Remember that the value for little g is equal to 9.8 meters per second squared. That can be approximated to 10 meters per second squared for doing, easy calculations. If you're doing a calculation on the AP test, you can use 10, and that's perfectly acceptable. It just makes your life easier. You can do that. There's also elastic potential energy. So elastic potential energy is energy that's stored in something that is where you change its shape and it will return back. So if you take a rubber band and stretch it out, it'll go back to its original shape when you let it go. Or if you compress a spring and then let it go, it goes back to that. So that's the elastic potential energy. And so I'm going to use PE, and then it's either E for elastic or S for spring. I'm not sure which is best to use. Let me just do that as S. And I should also look on your AP formula sheet. They might use U for potential energy, so they might show US on there. And so for a spring, it's 1/2 times K times delta X squared. Okay, so K is equal to the spring constant, which is a number that tells you how stiff the spring is and how hard it is to push it to get it to change its shape. And then delta X is the compression distance or stretch distance. Okay, so it's that change in length from the original undisturbed length. So if a spring, before you push on it, is 10 centimeters long, and you push it together so that it's only 8 centimeters long, then delta X would be 2 centimeters. So those are the three kinds of energy that we deal with all the time. Okay. Now, we like to talk about systems. So this has been a change, I think, in physics teaching in general, talking about systems in the AP 1 test. If you remember our AP classroom stuff, there's a lot of questions about systems on there. They bring up systems a lot. So remember, a system is just a collection of objects. So if we're talking about system energy, if we're thinking about kinetic energy, you just want to add up the KE for each object. Okay, now, but if we're going to be careful with the systems approach here, for the gravitational potential energy, the system is an object or objects and the Earth, the whole planet, because that is what's creating the gravitational field. So you have to have it in there. So if I have a book sitting on a shelf and it has 10 joules of gravitational potential energy, the most precise, most accurate way to say that is that there's 10 joules of energy stored in the book Earth system. So the book by itself does not have gravitational potential energy without the gravitational field of the Earth. So we're going to try to include the Earth in the system in that sense. And then for this we have, for the elastic, and again I've already changed notation here, so that could be PES, it might also be US. Basically there's almost never more than one spring in there, so it's a spring or rubber band or something like that. Now, as we said before, finding the energy of an object is okay, but what we usually look at is when things change over time about the energy. So this is the idea of work. Okay. So work is done when an object, I think I probably just said when a force moves an object over a distance, but that's kind of an oversimplification. So a work can be done by a force that's not actually making the object move. Okay, so let's look at all the forces on a box here. So we have a box here where friction is present. Okay, so we're going to have some sort of force F. Other forces on the box are going to be a weight force equal to mg. We'll have a normal force going in that direction, and it's moving this way. So it moves a distance here, d. And since friction is present, there will also be a frictional force. Okay, so if you look at our definition of work, remember the force has to be in the direction or parallel to the direction of motion. So in this case, the motion is along the x-axis. So the force has to be along the x-axis or have a component along the x-axis. So if we look at this situation here, as this box is moved this way, the normal force does no work. Because it is perpendicular to the motion. The weight force does no work. Okay. If we look at the force F, F is causing it to move, but not every part of it. So we need to think of the components of F. So there's an X component and a Y component. So Fy does no work, just like the normal force does no work. Fx does do work. So the work done by Fx is equal to Fx times d. Okay, but if we call this theta, a lot of people would say that's equal to F d cosine theta. So that's a formula that I think you'll see that. Okay. Now the other thing is that work can be positive or negative. Since F is pointed in the direction of the movement, it's moving to the right, Fx points to the right. So this is doing positive work. Okay, compare that to, say, the frictional force. The frictional force is doing negative work. If you think about pulling a box along with friction, friction is working against you. It's doing work, but it's doing it in the opposite direction. So that frictional force, the work done by friction, would equal minus F times D. Okay? So if you look at this idea, we need to consider the net amount of work done. Okay? So if we talk about the net amount of work done, that's going to produce a change in energy potentially. So the net amount of work, so in this case, we have the work energy theorem. So the net amount of work is equal to the change in kinetic energy of the system. Okay? So this is a big idea here, that work produces changes in energy. So in this case, if we look at it like if we have constant speed, for example, then what do we know? If something's moving at constant speed, F net equals 0. So the work done by the frictional force, the negative work done by the frictional force is equal to the positive work done by Fx, and so we end up with a net force, a net work of 0. So if we say basically F d cosine theta minus F frictional force times d is equal to 0. And so we have constant speed, so we have no change in kinetic energy. Makes sense. Okay. If it's accelerating to the right, then that means Fd cosine theta minus Fd is going to end up being our change in kinetic energy, or 1/2 mvf squared minus 1/2 mvi squared. Okay. All right, now to connect the idea of work to the idea of conservation of energy here. So this is a big idea. Work by internal forces do not change the mechanical energy of the system. External forces do change the mechanical energy of the system. Okay, so let's look at some examples of that. And I think my first one here is weightlifting. One of the classic examples I use when we talk about work and energy. So some person's going to take this barbell and they're going to lift it over their heads. Okay. So the first thing we want to do is just define what the system is. Okay. So the system, So the system is the barbell we're going to have the earth, and the next question, of course, is should I include the person in the system? Okay. I am not going to include the person in the system. So I just want to talk about the potential and kinetic energies of the barbell. I don't want to talk about the person. And this brings up a subtlety. So when we talk about the person, okay, the potential energy of the person is really complicated because there's all this chemical energy that we can change into other forms of energy and all that kind of stuff. So when we lift weights, we're undergoing a lot of energy transformations. And that's just not something we want to complicate this with. So we're only going to look at this So when we look at the energy right now, so we look at the three kinds, okay? So we got KE equals 0, nothing's moving yet, okay? We've got the, I'll use U for any elastic, of course not, okay? How about the gravitational potential energy? That's equal to mgh, but h here would equal 0, so we've got no energy in the system. Okay. Now, the person picks up the barbell, and let's say that is 2 meters right there. And let's give the barbell a mass, nice convenient number, 100 kilograms. Okay, so we still have the barbell and the earth as the system. Okay, so at this point it's at rest. There is no kinetic energy. We know that no energy from a spring, okay, but now we do have gravitational potential energy equal to mgh. So that's going to equal our 100 kilograms. We'll use 10 for little g, make our lives easy, and 2. So I believe that would be equal to 2,000 joules of gravitational potential energy in that system. Okay, so the question is, how did the system gain that energy? We went from 0 system energy to 2,000 joules of energy in the system. Well, a force must have done some work. Okay, and so basically, if you think about it, okay, how did the barbell get up there? Okay, the upward force is external. It's being exerted by an object that's outside the system. So the force on the barbell is being exerted by the person who's outside the system. So the upward force is external. So its work changes the system energy. And the amount of work is equal to that change in energy. Okay, so the 2,000 joules of work would equal 2,000 joules of energy. Okay, so now the person is done. They drop the barbell. If you've ever seen those, I don't know if they show weightlifting on TV anymore, but sometimes when they do one of these, if they're going for a world record, they just step out and they drop the thing. Okay, they don't bother to put it down gently or anything like that. Okay, so at this point, this barbell is traveling downward with some velocity. So this is the instant just before it hits the floor. Okay, so our system is still the barbell and the earth. Okay, and so we have, is there kinetic energy there? Yes, there is kinetic energy there, equal to 1/2 mv squared. We have no spring energy, and we're basically back down to E0, so we have 0 gravitational kinetic energy. Okay, so now the question is, did the system energy change? Well, if we look at the force that brought the barbell down, okay, the downward force which is gravity, since the Earth is in our system, is internal. Okay, so that internal force is not going to change the energy of the system because the Earth is part of the system. So that means that the system energy is still equal to 2,000 joules. And so what that means is that's all kinetic energy. So now we have 2,000 joules is equal to 1/2 times the mass, which is 100 times v squared. Okay, let's look at another example. And this one we have a spring and a block attached to the spring. It's a classic setup here. And if we ever get the next slide, there we go. Alright, so we've got a system here of a block compressed with a spring. We have block mass equals 0.1 kilograms. Okay, we're going to say that the spring constant K is equal to 50 newtons per meter, and we are also going to say that the delta X is equal to 0.1 meters. And so now we are going to, if we look at this system here, we have a place, this is frictionless. Except for this part where there is a coefficient of friction equal to 0.1. And we're going to say this distance here is 1/2 meter. Okay, so basically we've got the spring compressed. We're eventually going to let it go. The block is going to slide. It's going to hit this part with, it's going to be frictionless for a while, hit the part with friction, and then continue on. So the system, the question is what to include in the system. We'll definitely have the block, okay, and then we will have the spring. Okay, I'm not going to include the Earth simply because it's pretty clear from here we have no changes in gravitational potential energy, so we really don't have to worry about that. Okay, so if we look at this, we have energy stored in the spring. At this moment it's not moving, so no kinetic energy. We do have potential energy in the spring equal to 1/2 K delta X squared. Hopefully I pick numbers I can do in my head. So we've got 1/2 times 50 times 0.1 squared. So we're going to have 25 times 0.1 squared, which I believe would equal 0.25 joules of spring energy there. Okay. So now we let it go. Okay. And so the spring is now, it's not compressed anymore. The block is not connected to it. So the question is, what velocity do we have there? So we have a velocity, so let's ask ourselves these questions. What force acted on the block? Well, the spring force acted on the block. Is that internal or external? Well, the spring is part of the system, so that means it's internal. So what that means is that the system energy stays the same because internal forces, so we have to have 0.25 joules of energy in that system. Now, I didn't work out all these numbers beforehand, so I'm hoping this actually works out. So if we have the system energy here, that is all kinetic energy in this part of the system, so we're going to have 1/2 mv squared, so 1/2 times 0.1 times v squared. So we're going to have 0.25 joules is equal to 0.05 v squared. So v squared is going to equal 5, which means v is equal to the square root of 5. And it's going to take me a second. Well, I'll just leave that. Okay. So v is equal to the square root of 5. Okay. All right. So now this thing is going to move, and it's going to travel through this area with friction in it, and hopefully have enough energy to get to the other side. Like I said, I didn't actually do the math here, so hopefully this works out. So we know that mu here was equal to 0.1. That's our coefficient of friction, and we know our distance, we said, was equal to 0.5 meters. From there to there. Okay. So now, when we look at this in between these 2 points, while it was there, what force acted on the block? Well, that was friction. Was the friction internal or external? Okay. Oh, the friction was external because the ground is not part of the system, so that's external. All right. So how much force how much work did the force do? So the work done by friction is equal to the frictional force times the distance, and the frictional force would be the coefficient of friction times the normal force, and times the distance. And I think I'm going to get in trouble here because we're going to have 0.1. Okay, our mass there was our normal force is going to equal mg. M was equal to 0.1. And we'll use 10 for g, so that ends up being 1 times a d of 0.5. Oh, we're going to be okay. So that's going to equal 0.05 joules of energy. Okay, so that's going to be negative work. Okay, if you want to put a sign on that, you could. Okay, so that is energy that left the system. So if you think about friction, it was changed into thermal energy or some sort of energy that's no longer part of the system. So that wasn't. This is not a force that's adding energy to the system. Like in our barbell example, the work done by the person lifting added energy to the system. This is a case where energy was taken out of the system by friction. Okay, so the new energy of the system is, what was our from the previous page? I think it was 0.5 joules. I don't want to take the time to go back. So that means the new energy of the system is 0.45 joules of energy. And so now when we find the resulting speed of the block, okay, all the energy now is here is kinetic. So Ke is equal to 1/2 mv squared. So we have to have 0.45 joules of kinetic energy is equal to 1/2 times 0.1 times v squared. And I'll let you guys do the math if you need to prove that. But that's the idea here. So here we have an external force taking energy out of the system. Okay. So there are two things that I want to talk about that are just kind of miscellaneous topics here. One is work and finding the work from a graph. Okay, a classic example of this is a spring. So So when we do this, the idea is that work, if you remember on a graph, if we make a graph of the force versus the distance, okay, or position, I guess is the way to say that, okay. So if we have a force that's not constant, if it changes over this, so if we have something like this, okay, and we want to know how much work was done on the object, remember that the work is equal to the area. So if we have rectangles and triangles, we can easily calculate the area. Okay. A classic example of this is the work done on a spring or by a spring. Okay. So if we talk specifically about springs, okay, we know that that force on a spring is equal to K times X, or delta X. Okay, so when the spring is not compressed, there's zero force it takes to do that, and this is a linear function right there. And so what you get is that the work done by that is equal to the area, and so we have the area of a triangle. This is delta X right there. This distance is equal to the force, which for this spring is equal to K times delta X. And so the area of a triangle is 1/2 base times height. So you see you have 1/2 times delta X times K delta X, where you get 1/2 K delta X squared. Oh, but see, that work done on the spring ends up as energy stored in the spring. So there you go. You end up with that formula for the energy of a spring is 1/2 K delta X squared. Okay, and the last thing is just a quick reminder of what power is. So power, remember, is the rate at which energy changes. Or energy changes could also be work is done. So the formula, remember, is power is delta E, the change in energy, over the change in time. Okay, so I always go to the weightlifting example. So if two weightlifters lift the same amount of weight, to the same height, they both do the same amount of work, but one may do it very, very quickly. The other one may struggle and take longer to do it. So just remember what that is. Okay, so hopefully this little talk about systems and energy was a good reminder for you. Thank you.